How do we apply Newton's laws on a system of multiple masses connected by tension? Well, this can be done a long way and a short way. I will show you the shortcut, but of course I'm going to show you the longer way first. Let's begin by doing a free body diagram on each mass. I'm going to refer to this one as mass number 1, and I'm going to refer to this one as mass number 2, which means this is going to be weight 1 equals mg. Notice I'm using weight instead of F sub g. You could use either of those. So I'm using weight this time around because it's easier to put a subscript. Weight 1 equals m1g. I'm going to have tension pulling this block to this way, because once I set this in motion, the acceleration is going to look like this. We're going to have this block accelerate downward, and then we're going to have this block accelerate to the right. So there's a tension force along that's pulling it. I also have a normal force from the tabletop. Let's calculate weight 1. It's going to be 4 kilograms times 10, which is 40 newtons. Now, if you go over and focus on the object mass 2, you'll see that it has a tension force going up. Remember, tension always pulls away from the mass along the rope. So this time it's pulling up. And it also has a weight, but this time we're going to call this one weight 2 because this is mass 2. And weight 2 is going to be mass 2 times g, which would be 2 kilograms times 10, or 20 newtons. Now, since there is no friction, it's a frictionless pulley and it's a frictionless system, tabletop. Everything's frictionless. What that means is there's nothing to resist the acceleration of this thing. It makes this force here the causing force, and it makes this force here an opposing force. Think about how that works. Weight is going in the same direction as acceleration. Therefore, weight is a causing force. Tension is going in the opposite direction of acceleration. That makes tension an opposing force. Do the same thing over here. Tension here on this block is going the same direction. So that makes tension in this example a causing force. Here, since there is no force going to the left, the opposing force for this one is going to be 0. There is none. Okay, so we're going to just do these one mass at a time. Mass 1 and mass 2. For mass 1, we have causing force minus opposing force equals m1a. Well, what do we know? There's no opposing force, and we have tension equals m1a. Okay? That's all I can do at this point because I don't know A and I don't know tension. All I know is the mass. So I'm going to come up with a next equation over here in part B. I'm going to do this in a different color. Okay, over here for mass 2, my causing force, I'm going to go causing force minus opposing force equals m2a. Well, my causing force, remember, was the weight, gravity. So it's m2g, or I should say weight 2, minus the same tension. This is the same tension because it's the same rope, and it's the same pull on the same rope, but it's pointing in opposite directions. This time we're subtracting that tension, right? Equals m2a. Well, here's what we do. Since tension has a value of m1a, we're going to substitute m1a right here in place of tension. And this becomes weight 2 minus m1a equals m2a. Lastly, let's go ahead and add m1a over to this side, and we get the following. We get that weight 2 is equal to m1a plus m2a. Since the factor that is common to both of these is a, we can factor out an a, and this becomes weight 2 is equal to mass 1 plus mass 2 times a. Now, this was the long way to do it. And if that seemed kind of confusing, let me just tell you there's a much shorter way. Let me show you what that shortcut is now. The shortcut to get this exact same equation, okay, and by the way, once we get to that equation, what do? We divide by the sum of the masses to get acceleration by itself. So acceleration would be weight 2 divided by the sum of m1 plus m2, which is 20 newtons hanging over the edge. And the sum of the masses would be 6. That would be 3.3 meters per second squared. But how do we get this equation much faster without going through all of this? Here's what we do. You ignore tension because tension is an internal force pointing at each other. And since tension is pointing at opposite directions, tension will algebraically cancel. That's exactly what happened over on the left-hand side. In other words, we're only going to focus on external forces, like gravity in this case, and any force going to the left in this case. Now, we're not going to count gravity and normal force in this example because we're accelerating to the right, and those two forces are perpendicular, not parallel to acceleration. So we only care about forces that are going with acceleration or against acceleration. So what we do is we apply our Newton's second law. But our Newton's second law for multiple masses. And here's how it's going to work. It's going to be causing force minus opposing force, but it's going to be equal to the sum of your masses, sigma. This, for those of you that have never seen that before, this little thing that looks like an E is the Greek letter sigma, and it stands for sum, adding. Okay, so what are we doing? We're adding our masses, adding all the masses times A. Now look in this example. The weight was the ultimate causing force. Minus, well, an opposing force to the system would be any force going over here to the left-hand side. And since it doesn't exist, we get to cancel the opposing force this time. Equals, well, we're adding up two masses, 2 m1 plus m2 times A. And you can see we're getting the exact same equation, but much, much faster. Again, divide by the sum of the masses, and it's weight 2 over mass 1 plus mass 2. Weight 2 was 20 newtons over 2 plus 4, which is 6 kilograms. 20 divided by 6 is 3.3 meters per second squared. Example 5. What is the acceleration of the system below? Now, it's left in variable form, but let's go ahead and make this concrete. And let's say mass 1 is 1 kilogram and mass 2 is 2 kilograms. Okay. Now, the first thing we have to do is we have to label our forces. This would be weight 1 equals m1g and tension going up. This one would be weight 2 equals m2g, and this would also be tension going up. Remember, focus on, if we're talking about the acceleration of the system, we're going to apply the shortcut this time. The shortcut only involves external forces. You ignore tension. Well, the only external forces here would be your two weights, because if mass 2 is bigger, then mass 2 accelerates downward and mass 1 accelerates upward. What does that mean? Weight 2 is a causing force to acceleration, whereas weight 1 is pointing down, while block 1 is accelerating up. So weight 1 is an opposing force to acceleration. Okay, so we're going to go Newton's second law equation, causing force minus opposing force equals sigma ma. Remember, sigma m means to add up your masses. This case, there's only 2 masses. So the causing force is the weight 2 minus the opposing force, that's weight 1, equals the sum of your 2 masses, m1 plus m2, times A. Okay, now to solve for A, we again have to divide by the sum of the masses. And then at this point, we can just go ahead and plug in. Weight 2 is going to be, well, we didn't calculate yet, did we? Okay, so weight 2 is going to be mass 2, which is 2 kilograms times 10, or 20 newtons. Weight 1 is going to be 1 kilogram times 10, or 10 newtons. So we're going to go 20 newtons minus 10 newtons all over the sum of the masses, which would be 1 plus 2, or 3. So 10 newtons divided by 3 is also about 3 1/3 meter per second squared. Newton's third law. Newton's third law is something that we're going to be taking a look at between 2 different forces specifically. So Newton's first and second law really only apply to the forces acting on one object only. Newton's first law would be the forces acting on an object to make it go at a constant speed, therefore those forces are balanced. Newton's second law, on the other hand, are the forces acting on one object that cause the object to accelerate because those forces are unbalanced. That's what we've learned so far. Newton's third law is a great way of summarizing the fact that forces are always interactive between 2 different masses. And Newton's third law gets into account what those 2 masses are. Okay, and basically it tells you that every force has an equal and opposite force. If you hit something really hard, that something is going to hit you back with equal and opposite force. This is also known as an action-reaction pair of forces. Action force has an equal and opposite reaction force. Remember, ladies and gentlemen, again, this applies to 2 masses acting on each other. Example, a 10-kilogram child in a 5-kilogram wagon is pulled by her 80-kilogram father to the right with a force of 8 newtons. What is the magnitude and direction of the force on the father? So let's draw that. I'm not going to draw the whole wagon and everything, but let's draw that force. We have a force of 8 newtons. Okay, and what is this? This is the force of the father on the wagon. It's the force of the father pulling the wagon, right? So what's the magnitude and direction of the force of the wagon pulling back on the father? Well, it's equal in magnitude, opposite in direction. So it's 8 newtons to the left, because the father was pulling to the right. Example 2. Matthew has a mass of 85 kilograms. Part A. What is the force of gravity by Earth pulling downward on Matthew? Remember, the force due to gravity is going to be an mg calculation. So m is 85 kilograms times g was 10 newtons per kilogram. And we're getting 850 newtons of weight. Part B. This is the action force. So gravity, Earth pulling downward on Matthew, is the action. The reaction is Matthew pulls up on the Earth with a force of 850 newtons. Okay, so the action force is Earth pulling down on Matthew with a gravity force of 850 newtons. Matthew, in turn, applies a force upward back on the Earth of equal magnitude, opposite direction, also 850 newtons. Part C, what's the acceleration of the Earth due to Matthew's gravity? Well, we have net force equals ma. Okay, so divide by m, and A is equal to net force divided by mass. The net force is 850 newtons. Now the mass, well, that's going to be Earth's mass. Let me share that with you. Earth's mass is pretty big. It's 6 times 10 to the 24 kilograms. If we divide those two, we get an acceleration. Go ahead and pause the video and throw that in your calculator. We get an acceleration of 1.4 times 10 to the negative 22 meters per second squared. What is this number really? This is equal to 0.0000000000000000000. I'll have to come down here. 000 000 14. That's a lot. That is a lot of zeros and a super small number. Okay, so what this means is Earth's acceleration, Earth's upward acceleration is so small because Earth's mass is so large. It's too small to measure. It's even too small to notice, for that matter. Friction. Well, friction always opposes motion. Sometimes friction, as we're going to find out, also prevents motion. Factors affecting friction. The first factor would be the type of surface. Well, the type of surface, meaning what two surfaces are interacting with each other. It is, if it's like a car riding on the road, it would be the rubber tires against concrete, right? Maybe it's wood on sandpaper. Maybe it's wood on wood. Maybe it's wood on glass or rubber on glass. So the two substances, okay, the type of surface of the two substances need to be taken into account. That's one thing that affects friction. Now, we have a value that quantifies the stickiness or roughness between two surfaces, and it's called the coefficient of friction. Oops, I accidentally erased that. The coefficient of friction. The coefficient of friction is denoted by this Greek letter mu. Okay, now how do we draw this? It kind of looks like the letter U, doesn't it? Except it has a little kickstand out in front. Some people say it kind of resembles a letter M also. Whichever. Okay, very easy to draw. But the letter mu is the coefficient of friction. And again, mu measures the roughness between two surfaces, or you could think of it as the stickiness or adhesiveness between two surfaces. It's going to range from 0, which is frictionless, to 1, which is really a high value of friction. Okay, so most values of mu are going to be some decimal, like 0.15 or 0.30 or 0.50, some value less than 1. The higher the mu, the higher the coefficient of friction, the more friction. Now, what else affects friction? Well, think about it this way. If you had two boxes filled with books, one had, let's say, 2 books in the box, and the other had 20 books in the box. Well, the heavier box is going to be much harder to slide on the floor. So clearly weight is a factor. But as we've come to find out, it's actually not weight that affects the friction. It's the force of the surface applied up on the object, or the normal force. So friction depends on mu, which is the number that quantifies the adhesiveness between two surfaces, and the normal force. So we put that together into an equation. Friction equals mu times normal force. This is a really easy equation to remember. Friction is fun. Do you guys see the fun? F-U-N. Friction is fun. That is going to be an easy way to remember that equation. Let's identify the variables. F is the friction force. Friction force is in newtons. Mu is the coefficient. Coefficient is just a fancy math word for number. So this is like the friction number, coefficient of friction. It's not the friction force, but it's the value of friction that tells you how sticky the two surfaces are. And there's no unit for it. It is a unitless number. And N is normal force. Also in newtons. So if we take that equation and we solve it for mu, we see that mu is equal to friction force divided by normal force, which means newtons divided by newtons cancels, leaving you with no unit for mu. That's how we get no unit. Let's take a look at the next example. The coefficient of friction between a 2 kilogram wood block and a table is 0.3. So 0.3 is our mu. 2 kilograms is our mass. If the block is pulled by a force of 12 kilograms, that is our F. What is the block's acceleration? We're looking for A. Let's draw a picture of this. We have a surface. We have the block. It's being pulled with a force of 12 newtons. Since it's a 2 kilogram block, we have the force due to gravity, which is going to be 2 kilograms times 10, which would be 20 newtons. Since the normal force going up balances gravity, normal force will also be 20 newtons. Lastly, we have the force of friction. The force of friction is going to be, what's the equation? Friction is fun. F equals mu times normal force. Well, how about this? Off to the side, let's calculate the friction force. We're going to need it. Mu was 0.3 and normal force was 20. Well, 0.3 times 20 is 6 newtons. So we have a 6 Newton normal force going to the left. 6 Newton friction force, going to the left. Now we're ready to use Newton's second law. Newton's second law again tells you causing force minus opposing force equals ma. Solve for A, we divide by mass. And acceleration equals 12 newtons minus 6 newtons divided by mass. What's the mass? 2 kilograms. That would be 6 newtons divided by 2 kilograms, or 3 newtons per kilogram. You could also write that as 3 meters per second squared. Either one is fine. To further expand upon the idea of friction, there are 2 types of friction: static friction and kinetic friction. Static friction, ladies and gentlemen, is the type of friction that prevents an object from moving. Every time you take a step on the floor, It is static friction between the soles of your feet and the ground that prevent your shoe from skidding and sliding. Thus, you're able to push off the floor and move forward. Imagine walking on a frozen pond. You have much less friction because ice is a lot slipperier. It has a lower coefficient of friction, therefore the static friction acting on your feet, on the soles of your shoes, would be less. You'd have to walk significantly slower in order to not slip. That's static friction. Static friction prevents motion, prevents sliding. Kinetic friction, the word kinetic means movement. So kinetic friction is sliding friction. It's the friction that happens when one object slides or skids across another object or a surface. The skid marks of tires when brakes lock and the skid marks that get left on a ground when an accident occurs and somebody locks up their brakes, that's a perfect illustration and example of kinetic friction. But kinetic friction can be really seen with anything that slides or skids across a rough surface. It opposes the direction of motion, while static friction prevents that motion entirely. Both of them go opposite the force that is trying to cause motion. Now, static friction is always going to be greater than kinetic friction, and that's because if you think about it, it's much harder to start an object on a rough surface, start pushing an object on a rough surface and get it moving. It's harder to get it moving than it is to keep it moving. Let's take a look at the next example. The coefficients of friction between a 20 Newton block and a table are mu sub s and mu sub k equal to 0.4 and 0.25 respectively. Now mu sub s is the coefficient of static friction. Mu sub k is the coefficient of kinetic friction. Notice, if static friction is higher, your coefficient of static friction is always going to be greater than your coefficient of kinetic friction as well. Part A, what force is necessary to start a 20 Newton block in motion on the table? B, if the block is stationary and a 5 Newton force is pulling the block to the left, what will be the force of friction on the block? Finally, C, what force is necessary to keep the block moving at a constant speed? First thing we need is a diagram. So let's draw that. We have a surface, block. We have an applied force going to the right. We have a normal force going up. We have a weight of 20 newtons. So if the force of gravity is 20 newtons, remember, gravity is equal to mg, and therefore the mass is going to be the force of gravity divided by g. So 20 newtons divided by 10 newtons per kilogram would be 2 kilograms. We're going to need the mass. Since the gravity is 20 newtons down, the normal force is going to be 20 newtons up. Those forces are balanced. Okay. Now part A, we do have a friction force going the opposite way, and F equals mu times normal force. Friction is fun. For part A, it's asking what force is necessary to start the block in motion. So, in other words, the block is at rest. The block is currently at rest. And in order to start it in the motion, you must exceed the maximum static friction force. Okay, well, let's figure that out. The maximum static friction force would be mu times normal force. Well, coefficient of static friction is 0.4 times the normal force of 20, and 0.4 times 20 is 8 newtons. What this means is F is at least 8 newtons to the right in order to start the block into motion. Part B. If the block is stationary, well, stationary is not moving, and a 5 Newton force is pulling to the left, that's a typo, ladies and gentlemen, it should be to the right. Go ahead and change that. 5 Newton force is pulling to the right. What will the friction force pulling to the left be? Well, 5 newtons is less than the maximum static friction of 8 newtons. So what that means is if we're pulling with a force of 5 newtons to the right, that means the frictional force to the left this time has to be 5 newtons. You have to balance in order for the block to not accelerate. So 8 newtons was the maximum static friction, but you can have values of static friction that are less than the maximum depending on how much less force you're pulling with. So F equals little f, which are 5 newtons. And then part C, what are we going to do? What force is necessary to keep the block moving at a constant speed? So constant speed, we're moving it now. So constant speed, the block is now moving, which means now we're going to be using the kinetic friction because it's sliding across the tabletop. So we've got the thing in motion, and what's it going to be moving at a constant speed? Well, constant speed means forces are balanced. So if we look at this, the force going to this right has to balance the friction force equals mu times normal force going to the left. So F equals friction, which is mu times normal force, but it's mu sub k this time, because now we're talking about kinetic friction because we're sliding. So it's going to be 0.25 times that same normal force of 20 newtons, and a quarter of that of 20 newtons would be 5 Newton force. In this last example, we have a 2 kilogram block is being pulled by an 18 Newton force up at an angle of 30 degrees above the horizontal. The coefficient of friction between the block and the plane is 0.3. Find the acceleration of the system. Okay, since we're finding acceleration, we're dealing with forces, this is going to be a Newton's second law problem, at least horizontally speaking. In other words, we're accelerating this way. First thing we should do is draw the forces acting on this block. The force due to gravity is the weight, mg, and that's going to be (20 newtons). Now we have to be careful. Although we have a normal force pointing up, normal force is not 20 newtons. Okay, and the reason it's not balancing 20 newtons is because you have an upward force here that's also contributing to an upward total force. So the two upward forces are going to balance 20 newtons, not just the normal force. You'll see in just a second. We have friction opposing our motion, right? We're moving to the right, so friction is going to the left. And the friction equation is mu times normal force. Now, the last thing we need to do is we need the components of this, and we need to make a right triangle out of it. Remember what we did last time. We have the adjacent side, which is hypotenuse times cosine of the angle. And then you have the opposite side, which is hypotenuse times sine of the angle, where the hypotenuse is the 18 newtons. So let's fill this out. This side is going to be 18 cosine 30. And this one's going to be 18 sine 30. The opposite side, the 18 cosine 30, when we put that in our calculator, we get about 15.6 newtons going horizontally, going in the x direction. When we put 18 sine 30 in our calculator, we get 9 newtons going up. Now, in order to find acceleration, I'm going to split this in half here. To find acceleration, we're going to use Newton's second law, which, if you remember, was net force equals ma. That was the equation. But we wrote net force as causing force minus opposing force equals ma. Now the causing force is going to be this blue force here, that 15.6 newtons. There's your causing force right there. Why is this the causing force? Because we are accelerating to the right and causing forces point the same way. That makes friction the opposing force. So since friction is going to be that opposing force right there, we need to find friction. Otherwise, we're going to have a hard time continuing the problem. Now, friction would be a vertical force. Friction, in order to find friction, friction's a horizontal force, but friction involves normal force, which is a vertical force. So we have to start there. Deal with our vertical forces. Now, the forces in the y direction are going to be balanced because the block itself, this block is not being pulled off the table. It's not accelerating upward, it's accelerating horizontally. So what this means is we're going to take forces up and set them equal to forces down in the y direction. Forces up, well, there are two of them. There's normal force, and there's the opposite side of the triangle there, which is the 9 Newton force. So normal force plus the 9 newtons equals the downward force of gravity, which is the 20. Subtract the 9, and normal force is 11 newtons. Okay, now, if you recall, friction was equal to mu times normal force, and we were told mu, the coefficient of friction, was 0.3. So 0.3 times 11 is going to be 3.3 newtons of friction, and once we have that, we're ready to proceed. We have 18 cosine 30 minus friction equals ma. Divide by m, and we have 15.6 newtons minus the 3.3 newtons divided by our 2 kilogram mass, and we get about 6.2 meters per second squared.